normal distributions. Okay. And so the first step in doing this is that you calculate a pooled probability. This is just like doing the two-sample t-test. Right? We calculated the pooled variance. So here we're calculating the pooled probability, and that's just equal to n1 p1 plus n2 p2 over n1 plus n2. It's a weighted average of the probabilities. Another way of writing this is that it's just x1 plus x2 over n1 plus n2. Okay? And here, x1 is just 13. x2 is just 7, divided by the total, which is 5,000 plus 10,000. And when you do that, you get 20 over 15,000, which is 0.00133. So that's our pooled probability. We then calculate our pooled variance. Which is just p hat 1 minus p hat times 1 over n1 plus 1 over n2. So that's the second step. Calculate the pooled variance. So we calculated p hat already from part A. That's just 0.00133. So when we do out this algebra, just plugging in 0.00133 for p hat and n1 and n2, what we get is, I didn't calculate it out, but for some reason I don't have that number. But you guys can just plug in the numbers. Now, the last step is do which test? What test are we going to do here? Are we going to do a t-test or a z-test? We're comparing two samples, right? What are we going to do? Well, we're comparing two binomial samples, both of which have NPQ greater than 5. So both of which we can assume are normal. Therefore, we use the z-test. Okay? So step 3, calculate z. Okay. Z is just equal to p1 minus p2 all over the pooled standard deviation, and that's equal to p hat 1 minus p hat times 1 over n1 plus 1 over n2. It's that number over there that I didn't calculate. Alright. And so we have all those numbers. We plug and chug into an equation, and we get that this is equal to 3.0. So we're doing very similar steps to the two-sample t-test. We calculate the pooled variance, but the way to do that is by calculating the pooled probability here. Okay? And then we take that pooled variance and calculate the z-statistic. That's it. We get a value of 3.0. When you look this up in the back table, is this a one-sided or a two-sided test? It's two-sided. Remember, we're not looking for greater than or less than. We're just looking for a difference here. So it's a two-sided test. So when you look this up in the back normal tables, our p-value, okay, for this area right here, both of those areas are the p-value for a z of 3.0, right? That's what we're essentially saying is the p-value. It's the area of these two outskirts. When you look that up, it's equal to 0.0026. So what do we conclude? Do we accept or reject the null hypothesis? We reject it. I mean, this is much less than 5%, right? So we reject the null hypothesis, and we say that P1 is different from P2. So is everyone okay on comparing two samples of binomial proportions? Okay. So now the interesting things come about here. Now we're going to get into some interesting stuff. I know, you guys have been waiting patiently. But there's another way of doing this. There's a completely other way of doing this, and that's using contingency tables. So if we go to the next question, we're going to do this exact same question, but now using contingency tables. Okay. And what contingency tables is you put the data into a tabular form. And I'm going to show you how to do that. So we're dealing with the exact same question. So contingency table. So let's make a 2 by 2 table. And on the columns, let's put the disease. Here in this case, it's myocardial infarction. And either you have one or you don't. And on the rows, let's put whether the patient uses oral contraceptives or not. And either you use it or you don't. Okay. And the question said that of 5,000 people who used the oral contraceptives, so there's 5,000 out here, 13 developed the heart attack. So this must be 13 here, and this has to be 5,000 minus 13, which is 4,987. And then of the 10,000 they looked at who didn't use oral contraceptives, 7 developed myocardial infarction. And so that leaves 9,993 here. Okay. And then you can just fill in the rest. There was a total of 15,000 people in the study. 20 of them had heart attacks, and the rest didn't, 14,980. Okay. And we'll use the same notation that we used for our sensitivity and specificity tables. This is A, this is B, this is C, and this is D. Okay? And we're asking the exact same question. We're asking, are the two probabilities, P1 and P2, are they the same or they're different? Or another way of asking that, which is the buzzword for these contingency tables, is there an association between OC use and having a heart attack? That's the question. And you always use the word association when you're dealing with these contingency tables. So how do we do it? Well, it's the same way that we did it before. It's exactly the same setup. I'm going to show that. So first I'm going to tell you how we do it. So these are the observed values. This is what's observed in the data. But some of these are just fixed numbers. Like this is a fixed number. They chose 5,000 oral contraceptive users and 10,000 non-users. So these numbers are fixed. Those three there. If those are fixed, the question then becomes, what would we expect to see in this table? If there were no difference, if there were no association. So let's come up with an expected table, assuming that there is no association. If there is no association between oral contraceptive use and having a heart attack. Well, how do we calculate that out? Well, it's all based on these fixed values here, as well as these total values here. So, based on these outer numbers, you can predict the expectation values of each box, okay, assuming that there's no association. And I'm going to quickly put those numbers down. Here it's A plus B times A plus C over N. So essentially, it's the sum of the row times the sum of the column, all divided by N. So for B, it's A plus B times B plus D over N. For C, it's A plus C times C plus D over N. And for the last one, it's all it is C plus D times B plus D over N. Now, how do we derive that? How do we derive that? Well, this is the way to do it. Remember, this is assuming that there's no association. So what we're assuming is that P1 is equal to P2. That's the assumption. Okay? So let's calculate the pooled, or the average, P. Well, we already put that equation down. That average P is x1 plus x2 over n1 plus n2. And remember what those are referring to. This is x1, this is x2, right? It's just the number of people with the heart attacks. This is n1, this is n2, yep, the two different groups, okay? So let's convert this equation into our values A, B, C, and D. X1 is just A, X2 is just C, and N1 plus N2 is just the total N. Okay? So that's our probability there. Then, what we can say is that, what do we expect X1 to be? What do we expect? I'll call it A or X1. They're the same thing. It's just whatever's in this first box there. What do we expect it to be? N1P. Who said that? Yeah. We expect X1 to be just the number in group 1 times this average P. That's just like any binomial distribution. The average is n times p. Here we're dealing with group 1, so that's why we're calling it n1p. Okay? Well, what's n1? It's equal to a plus b, right? So a plus b times the p that we calculated is a plus c over n. And that's what we expect in the first box. You guys see that? And you can go back and do the same things for everything else. Let's see what do we expect of x2? x2 is just n2 times p. We know what n2 is. It's just c plus d. So c plus d times the probability a plus c over n. That's what we got. And you can do it for the other two as well. Yes?
So somehow this makes it way more complicated than relationship. You just say, okay, your
Yeah, exactly. So this is what you would expect if there was no association and given these constraints, right? And this is what we actually observe. So now the last step is compare the observed with the expected, and are those different? Now, why is that making it more complicated? Well, I was just deriving these equations. I don't know. I mean, those weren't. I don't know if those. I didn't see a very intuitive way of explaining those. But how did we get these expected values? That's what I was deriving. Now, well, let's go through the next steps. Okay. I mean, does everyone follow? So we have our observed. We now know the equations for our expected values. Let's calculate those and compare. Yep.
As you proceed, like making the assumption that you have good estimates for the incidence of MI in the population.
Yes, and as long as NPQ is greater than 5, you can make you can make those assumptions. Like, what are you asking exactly?
Well, you're calculating the expected incidence of each of these four boxes.
Right.
But underlying that, you made an estimate of the incidence of MI.
Absolutely. These expected values are all based on the underlying probabilities that you get from the observed.
That itself is going to be a random variable.
Well, you have to have confidence in your data. Like, you have to be willing to say that, yeah, I'm sticking my neck on the line and saying that these probabilities are reflective of the actual data, the underlying populations. So, and that's okay to do. We always do that, right? Because we're always dealing with smaller sample sizes in the population, right?
Although the statistics is not going to come to how bad over your estimate of the MI is.
Right. Silo, did you have a question?
No, I
Okay. All right. So the nice thing is that this doesn't have to be just comparing two proportions. When you do it the contingency table method, you could be comparing 10 by 10 tables. And that's the advantage of using this method. And so the expectation value of, I'll call this the expected value of any ith row and jth column is equal to the sum of the ith row times the sum of the jth column all over the total n. So you can extend this. So far I'm only showing it in a 2 by 2 table, but the real advantage of using this method is to going beyond the 2 by 2 table. And that's how you would calculate the expectation value at any given point. Okay? Nope, doesn't have to be. So, first step in doing contingency tables is make a table of the observed data. Second step is calculate the expected values. Last step, which I'm going to put this down now and bring this up. The last step is calculate the differences. And the way you do that is you take the observed minus the expected for each data point, for this one and this one. You take that difference and square it and divide it by the expectation value, and you add them up. Okay? And that follows what's known as a chi-squared distribution. Yes? Yes, for every point. So here you would get 4, because there are 4 different boxes, 4 little boxes. So you just do it for every box. This minus this squared divided by whatever that is, plus this minus this squared, and we'll go through it.
So the little I here right here is not the same as I for
Yeah, this little I here is not the rows, it's for each little box, where there are the number of rows times the number of columns. There are that many. Okay. All right. And chi-squared is dependent on the number of degrees of freedom. And the number of degrees of freedom, just like it's the same thing as a t-distribution in this sense, is just the number of rows minus 1 times the number of columns minus 1. It's that product. So if you're dealing with a 2 by 2 table, it's just 1 times 1, so that's 1. Okay? All right. Well, a couple of things that we need to add to this before we do carry out our example is, one, you can only do this test. You can only use this test if the expected value in each square, in each square here, is greater than 5. Again, we're assuming underlying normality. Okay, that's the reason for that. And if we go back to what a chi-squared is, a chi-square just looks like a normal distribution but squared. Is a normal distribution squared. So if we have a normal distribution, just say that looks like this. Okay. The chi-squared squares everything. Okay. So everything is now just in the positive quadrants. Okay. So the basis of the chi-squared is that it's a normal distribution squared, and that just comes from having this entire equation follows that chi-squared distribution. So that's one thing. You can only use this test if each square is greater than 5. The other thing is you need to add in a continuity correction. What the continuity correction is it corrects for the fact that we're going from a binomial distribution, which is made of discrete variables, to a normal distribution, which is made of continuous variables. And the way to do that is you change this equation. You take the absolute value of this, subtract a half, and square the entire term. Okay? So this number right here provides the continuity equation, continuity correction. And remember, the reason why we do that is because we're taking a binomial distribution and approximating it to be normal. Now, did we do anything different in the last example? Weren't we doing the same thing? Haven't we always been doing that? Like before we even started contingency tables, haven't we always been comparing two proportions and assuming, well, it's binomial, but NPQ is greater than 5, so let's assume that it's normal. So where were the continuity corrections in those equations? They actually do exist. Those continuity corrections do exist. They become more complicated, so that's why we don't present them here. Okay? But those continuity corrections do exist. Forget about it. Don't use them for those other tests. You use it here, though. I want you to remember to use it for the chi-squared test. Okay? All right. So then what do is you calculate this chi-square value. And what do you compare it to? Compare it to chi-squared of what? Is this a one-sided or two-sided test? It's a two-sided test, right? It has to be. Because our question is, are the proportions the same or are they different? So it's a two-sided test. And there's only one side of the chi-squared distribution. Because when you square it, all the values here on the negative side go to the positive side. So it's still a two-sided test, but you compare it to 1 minus alpha. Okay? because everything is now just on the positive end. Okay? So what I'm going to say here is, if the two probabilities are different here, okay, and you're looking at this area here, that area could either represent where P1 is less than P2, or P1 is greater than P2. That's represented by that one area here. Okay? So it's a two-sided test, but you only look at 1 minus alpha. All right, so let's carry out this test. So we would have to calculate these expectation values. These are just from the observed values, right? So the expectation value in the first block, let me say here, is just A plus B, so that's 5,000, times A plus C, which is 20, all over N, which is 15,000. And when you solve that, that is equal to 6.7. When you do the whole table, what you end up with are these values, and you should go back and calculate these out. You get 6.7, 13.3, 4993.3, and 9986.7. Those are the expectation values when you calculate it out. Okay? So given those, we then calculate the chi-squared, which the chi-squared, all it's doing is it's measuring the observed minus expected values. Remember, these expected values, we get them if there is no association between these two variables. Okay. All right? And so the chi-squared here, which is just a 2 by 2 table, so it's chi-squared with 1 degree of freedom, is going to be equal to the following sum. It's going to be the observed here, 13 minus 6.7, the absolute value of that, minus 1/2 squared, all over 6.7, plus the second block, 4987, sorry, the absolute value of 4987 minus 4993.3 minus 1/2, that value squared, all over 4993.3, plus the third value, 7 minus 13.3 minus 1/2 squared, all over 13.3, and plus the last value, which you guys can figure it out. Right, but that's how you set it up. There will be 4 terms in your summation, and what you end up with is 7.67. You compare this to chi-squared 1.95 in the back tables. It looks just like a T-table where you have degrees of freedom here, so you just go with the first one and you look at your values, and chi-squared of 0.95 is equal to 3.84. We got a value of 7.67, so we're much bigger than 3.84. So what do we conclude? We reject the null hypothesis. If I were to look at this chi-square table and calculate a p-value, I would look for where it falls at 7.67, and that gives me a p-value of roughly 0.005. That's our p-value. Okay? Now, does that agree with what we got before using the entirely different method where we used, what did we get before? .0026, right? And here we got a p-value of .005. Why are they different? They should theoretically be exactly the same. But there was one difference that I already mentioned between the tests. Here we used the continuity correction, and in the other test we did not. That's the only difference. Otherwise, both tests are exactly the same. And you might say to yourself, like, we went through a lot of effort here. You know, why would we do this method versus the other? Well, remember the other method you can only use when you're comparing two proportions. And here, we'll extend it to like many multiple, 10 by 10 tables, okay? So that's the advantage of this. If you do the exact same setup, you find the expected table, the expected values, and compare them using this chi-squared equation. That's all you have to do. You know, I didn't photocopy that, so I'll scan it and put it on the web for you guys to make a copy of.
Should we bring it to the...
You should definitely bring it to the exam.
So it's like 10 tables.
They are, but I want you to get comfortable using these, because the standard tables that are provided on the competent exam are from the book that she uses, which is different. I'll make photocopies of the chi-square table too, so you guys don't have to print them out yourselves. I'll just get them to you. I can't get them to you by tomorrow. I'll leave them out in the lounge. Okay? All right, we're not done yet. We're not done yet. Does this make sense though? So, when you're doing a chi-square test, you make your contingency table, your 2x2 table. Okay? And for the purposes of the exam, you need to know this method. Like on the exam, we could very easily say, compare these two proportions using the contingency table method. Even though you know how to use the other method, you need to know this method as well. Okay? So, you make your contingency table, then you calculate the expected values, compare the two using the chi-squared equation, and you're all set. Okay? Now, for a 2x2 table, this equation becomes a lot easier. And so you don't have to necessarily go through each step by step. For a 2x2 table, this chi-squared value for a 2x2 table is equal to n times the absolute value of AD minus BC minus n over 2 squared all over A plus B times C plus D times A plus C times B plus D. So everything we've done to calculate the chi-squared reduces down to this equation. So it makes it a lot simpler. So that's the shortcut when you're doing a 2x2 table.
We can just write that instead of...
Yep. You do not have to. Once you're at the stage where you have to calculate the chi-squares, you don't have to write this equation down at all. You can just go straight to this for a 2x2 table. That's all you have to do. It does. It does have the continuity correction. N over 2 here. It absolutely does. So this is exactly equivalent to this. You're just carrying out the algebra. You can prove it if you want. Fun Saturday evenings. All right, we're not done yet. I have to go over this last test, so it's going to take about 15 minutes. Okay? Any questions on this? Oh, one last thing. So this chi-squared test is also named after a person. It's called the Yates chi-squared test. Okay, so you'll see it called Yates. And remember exactly what this is for. You're comparing two different sample proportions. So could you use this test for paired data? You could, theoretically, but you'd be losing a lot of information, right? This test is for unpaired data. This test is for two completely independent samples. Okay. Now, we're going to get into the case of paired data and contingency tables, and that's called McNemar's test. So what we've done so far is for unpaired data. Now let's go into paired data. So contingency tables now paired. I'm going to erase this. And my plans for tomorrow is once we finish up with this test, which is called McNemar's test, we'll be done. And then tomorrow we'll go over odds ratios. And we'll talk, I don't know what you guys think. Should I talk about regression a little bit? What was that? It's not on the test. I already said that. It's not on the test. So what I do need to cover tomorrow is odds ratios and survival. That's the last two things. And I could talk about regression just briefly. I wanted to, but if you guys don't want to, I mean, I don't have to do it. I know this is information overload. The reason why regression is something that I don't really care about going over is because there's no way you guys really need to care about regression from a theoretical point of view. You're never going to do those calculations on your own. You're never going to have to know the equations. It's just too hard. You're going to have to use a software package for regression. And I can describe some of the theory, but maybe I'll go over it for about 15 minutes. How's that? We'll talk about it for 15 minutes. I'll show you some graphs, and you'll never have to worry about it again. That's regression tomorrow. The regression is not on the exam. What was that? No. It's going to be in the middle. It's going to be in the middle. Yeah, I know. You can leave in the middle if you really want to, but there's a logical progression. Like, I've got to do odds ratios next. We'll go into regression, and then I'll end off with survival analysis.
It might be good to do the stuff that we need on the exam course, so you have energy.
Yeah, I know, but then in the end, like, you guys are just going to leave after I finish survival, and you're not going to stay for the regression, which is fine. Okay, maybe I just won't do it then. It's okay. It's all right. All right, I'll do it at the end. You guys come in. It'll be just me and the video camera.
All those people in
Okay. So, are we okay with what we just went over, the contingency tables? Okay. There's a practice question on that in the problem set, so make sure you do that. And then, yeah. So now, we're looking at paired data. And let's do this in the context of an example. So get out the question on page 5 in our handout. And what we're looking at is, we're looking at two groups of patients. But each patient was paired. Okay? With another group, with another woman. So we have women that have breast cancer that were all treated with mastectomies and then subsequently given chemotherapy. And there were two types of chemotherapy, either treatment A or treatment B. Okay. And the outcome that they looked at was survival. 5-year survival post-mastectomy. And so either they survived or they didn't. Okay. And each of the patients were paired. But if we looked at the data, we found that 526 who got treatment A survived, but 95 didn't. And 515 who got treatment B survived, and 106 did not. Each one were a total of 621. for a total of 1,242 patients. So just by looking at the data in this form, would you say there's a difference between treatment A or treatment B? No. It's about the same. The amount that survived, 526 versus 515, that's most likely within normal error, okay, normal variation. So just by looking at the data in this method, you would say there's probably not a difference. Okay, and you could do your 2x2 contingency table and do the calculations, and that's what you would find. There would be no difference between the two groups. But the thing that they did is that they added, what is this not taking into account by doing the method this way? The pairing. Nowhere in this analysis have we done the pairing. So this method does not account for pairing or the paired data. Okay? But there's another way we can look at this data. That's by seeing what happened amongst the different pairs. So we make another 2x2 table. And on one side we put the outcome of treatment B. And on the other we put the outcome of treatment A. Either yes, they survived, or no, they didn't. And that's what this last paragraph is talking about. Instead of having a total of 1,242 people, now we're looking at a total of 621 pairs. And it says that of the 621 matched pairs, there were 90 pairs in which both patients died. So where would I put that data? Yeah, the lower right. 90 patients, 90 pairs where both patients died. So the outcome of treatment A was negative, as well as the outcome of treatment B. Okay. 510 pairs both survived. And of the remaining pairs, see, now we've only accounted for 600 pairs. We know that there is a total of 621. So what happened to the other 21 pairs? Well, 16 pairs in which the one patient on treatment A survived, but the one in treatment B did not. Okay? And there were 5 pairs where the patient on treatment B survived out to 5 years, but the patient on treatment A did not. So what does that tell us? If treatment A and treatment B were equal, what would we say about this data? I mean, what would we have to say about this table? Yeah, these should be equal, right? As many people who failed on this but survived on this should be the same as vice versa, if the two treatments are the same. So I'm going to introduce new nomenclature here. These two are called discordant pairs. Because the outcome of each treatment was different. All right, so a discordant pair is when you have a matched pair with different outcomes. The other two are called concordant pairs. And those are essentially just matched pairs with the same outcomes. Now we can call this, let's just call this a type A discordant pair. And we'll call that N sub A. Okay. And this, we'll call this a type B discordant pair, and we'll call that N sub B. Okay. And N sub A plus N sub B are just the total number of discordant pairs, n sub d. Okay? Now, if the two treatments were equally effective, if the two treatments were equally effective, as you guys had already said, n sub A would equal n sub B. Or another way of writing that is that n sub A is equal to half of the total, n sub D. I'll write that up here. N sub A should equal half of the total. Right? If the two treatments are equal. And so the question is this difference, 5 and 16, is that significantly different? So how do we do that test? Well, we use a chi-square test. Can I erase this side? Again, we use a chi-square test. And this is a 2x2 table. So the number of degrees of freedom are just 1 for the chi-square test. And what it's equal to is equal to this difference, n sub A minus nd over 2. This is observed minus expected, right? Minus a half for the continuity correction, squared. Okay. All over n sub d over 4. Now, if it were exactly equivalent to our past equation, it would have been observed minus expected divided by expected, which should have been n sub d over 2. Why are we using n sub d over 4? Yeah, they're all the same, sorry. I should have been using lowercase n, just for the number of people, number of discordant pairs. But why are we using n sub d over 4? Does it matter? It doesn't matter either way, it'll still follow a chi-square distribution, but the reason why we're using n sub d over 4 is, remember what I went back and told you. A chi-squared is what? It's just a normal distribution squared, right? And so what is this? What are we looking at? We're looking at the same thing as our sign test. I don't know if you remember that. The number of positive differences minus what we expect divided by the standard deviation. Right? So let's go back to that derivation. If we were to do a z-test here, right, it would be what we observed, it's n sub A, minus what we expect the number to be, n sub d over 2, all over the standard deviation. What's the standard deviation of what we expect? That's equal to the square root of n p q, right? Square root of n sub d times 1/2 times 1/2 is equal to the square root of n sub d over 4. Okay? So that's what we would, this is the test that we would use if we were doing a z-test. Okay? Well, a chi-squared is just the square of a z-test. And that's what we have here. It's the square of this over the square of this. And that's why we do divided by 4. And we have this added factor of minus 1/2 for a continuity correction. That's the only difference. So this point is illustrating two things. One thing is that it shows that in fact, yes, the chi-square distribution is just a normal distribution squared. And two, that the Mecklenburg's test is very similar in form to the sign test. So let's review what we've done so far. We've made a 2x2 table where we're able to look at the data as pairs. The concordant pairs are the ones where the outcomes were the same for each matched person, and the discordant pairs where the outcomes were different. The question is, are these discordant numbers equal, statistically equal, or are they different? Okay. Well, if they're equal, then one of them, this number, should be equal to the total divided by 2. Okay. So that's what we expect. We divide by this number, nd over 4, and calculate a chi-squared using this equation. Okay. When we do out the calculation using this example, it's just the absolute value of 5 minus 21 over 2, right? Minus a half squared all over 21 over 4. And so when you solve for that, you get that it's equal to 4.76. What do you compare it to if we are at the 5% level, 5% significance level? 0.95. This is a two-sided test, but remember we're dealing with chi-squared, so it's 0.95, not 0.975. And that's equal to 3.84. Okay? And so our number is greater than 3.84. What do we conclude? We reject the null hypothesis, which was? We're rejecting the null hypothesis that the number of discordant pairs is due to chance. That means they are statistically different, the number of discordant pairs here. And so what does that tell us? Which treatment would we use? Well, outcome of treatment A, right? More people survived on treatment A, 5, 10 plus 16, right? So treatment A is a better drug to use than treatment B. And that's the one that you would use. If you didn't pair the data, if you didn't go through the trouble of pairing the data, you would have missed that difference. Remember, when we just put down that other 2x2 table, the proportions looked equal. But when you pair the data, you add strength to your test, and you use the McNemar's test, and you show that there was a difference. Yes?
Do you know which of the two discordant pairs is used in your chi-squared?
Doesn't matter. It'll be the same thing. Doesn't matter. Yes?
Don't all of these paired tests, paired well? I mean, that there isn't, another variable that you totally neglected to account for that was not, for whatever reason, specifically present nicely in most examples.
Yeah. Well, actually, what I want to do is, since it's getting late, why don't we stop? Are there any, well, there are questions. You guys should just come up and ask me questions. Do the problem set, hopefully by tomorrow or not, and if not, hopefully soon. And we'll come back tomorrow. I'll quickly go through odds ratios and survival. That should take about an hour and a half. And then about a quick review over everything, which will be another 15, 20 minutes. And then if you guys want to stay for regression, I'll stay for 15 minutes. Okay. All right. See you tomorrow. You're welcome.
When you're doing paired tests, you're sort of hoping that your pairing is reasonable, and right? I mean, it blends statistical significance as long as the pairing is right. But if you just randomly pair it, then
Right.
you could have statistical significance.
Right, and in the question,
for no reason.
right, and in the question, you're trying to match for any other variable. So you're matching for age, sex, other clinical condition. So you match as much as you can, and then look for a difference.
Right.
And hopefully, that difference is due to just the treatments. But if you
Right.
didn't match well enough, it could be due to some other confounding factor. Right?
So you have to always say, whenever you're doing this, exactly what you matched for, and then someone could come along and say, it wasn't the treatment at all, it was this other
Absolutely,
factor."
absolutely. That happens all the time. Okay. Thank you.
If you can use the contingency table 2 by 2 in place of the two sample for knowledge collections, when would you choose to do the 2 by 2 contingency table versus this test?
Doesn't matter. They give you the exact same results. Probably this is easier. The only reason why you want to get comfortable doing this method is when you have more than just two proportions, when you're comparing a big set.
Alright, so but if you could create the situation, the 2 by 2 table, you can either do it this way or that way.
You
Doesn't
can.
matter. And the only difference is due to the correction factor.
Yeah, that's the only difference.
Alright, so
Otherwise,
what-
it's exactly the same. But
So
you need
what-
to know this method because this is the one presented in most papers.
Okay, so then
For some
maybe-
reason, people use this method the most.
Okay, so then it probably would be just get comfortable with this method and kind of forget about this. I mean, not that this is different from anything else. but-
Well, I mean, yeah, that's true for later on in the future, but for the purposes of the exam, we could ask you to do it using both methods. So we have the right to ask you to do it a particular method on the exam. Sure. Any other questions? Yes? Did you have a question? One question I have is, does anyone have a laptop I can borrow for tomorrow for this lecture? No one has a laptop? All right. I need a laptop. It just reduces to what?
Yeah, I swear, theoretically, you're doing very oh yeah, because it's just like, you have two numbers.
I mean, you know that in theory, this number should be compared to this sum divided by 2.
That's 5 is the tail system. What's the level that it's from?
Hey.
Wait. See? Why do you use distribution?
Because it says using the sample standard deviation.
Oh, okay.
That's all. So you have to take the sample standard deviation using these 4 numbers.
Okay.
I think you calculated it in part B.
Yeah, well, yeah, I did, but then, I mean, it's like, is it because...
Yeah, you're just assuming that you don't know 5. You don't know this number. That's all.
Oh, okay.
So it's just asking you to do it a different way.
Like, how do you tell to use one-sided or two-sided? I'm having on determining one-sided versus...
Well, this should be one-sided just because it's asking, how confident are you that it's 90 or greater?
Oh, okay. And...
It's not saying
Yeah,
that it's not 90. It's asking, how confident are you that it's 90 or greater? Yeah, so it's one-sided test.
I'll put this one on. Isn't it supposed to increase because, I mean, isn't n is going to increase because your alpha is...
So alpha is less stringent, so that means that you don't need as much of as large of a sample size to have the same power of the study. So if alpha is less stringent, you can theoretically get away with less of a sample size.
But that's kind of the opposite of what you just put in for C, though. Because for C,
But this is actually, no, here you're not dealing with alpha, here you're dealing with power, which is 1 minus beta.
oh, okay.
Oh, what did I put here? Oh, I mean, these are different ways of, how can one increase the how can one increase the power? So you can increase the power either by increasing the sample size or decreasing the standard deviation. It's all based on this equation. This is power, right?
Mm-hmm.
You can either increase the sample size,
Mm-hmm.
right? Or you can decrease sigma, Or you can make this less stringent, and the reason why, because there's a negative, when you go from 5 to 10%, you're actually, what are you doing to z when you're going from? You're decreasing the value of z, but because it's negative, you're subtracting less, so we're making power greater.
Okay.
Right. But here, now if we go to D, if you were making it less stringent, you're decreasing the value of z, so you're making this less negative,